Hi, my name is KWood, and I am an undergraduate in biomedical and electrical engineering at CSU. I have spent over 8 hours on campus today, which can only mean that I'm enrolled in all 3 of the classes for junior year, 311, 331, and 341. Today, I'm going to be talking about the power management system. First, I'm going to talk about with the 331 mechanisms of the circuit and the behavior of the diodes. Then I'm going to move on to a more physics-based approach with the view of the diode. And to end off, I'm going to look into the signal and system side of the circuit. Hope you enjoy the video. The power management circuit is composed of a rectifier region and an RC circuit region. The rectifier circuitry takes in an AC signal and outputs an absolute value of that voltage of the AC signal. This works the following way. The positive section of a AC signal goes into the circuit, shown by the red line. The signal cannot enter D4, but can flow through D1, assuming that the voltage is higher than the diode's threshold voltage. This current then flows through the resistors and capacitors. That I'll talk about later. It then enters D3 and returns to the power source. A similar path is followed with the negative portion of the AC signal, shown in blue. The current flows out of the source into D2, through the RC circuit, and through D4. It then re-enters the source. This results in only a positive voltage output, regardless of its sinusoidal nature in the input. Now, you may be wondering what the purpose of the resistors and the capacitors are. Well, the goal of the system is to turn an AC signal into a DC signal. While you can't truly get an absolute DC signal from an AC signal, you can get pretty close. We get very near to a DC signal by smoothing out the rectifier's output with an RC network. When the signal reaches the capacitor charges up, and then it slowly discharges until the next rectified signal hits. This creates a graph like the one shown. Now, the diode is made up of a P-type doped region and an N-type doped region. In a diode where there is an extreme external electric field applied, it changes the behavior of the diode. When there is a forward bias, the P side of the diode has a greater voltage than over the N-type side, which allows current to flow through the diode. In reverse bias, the voltage over the N-type is greater than over the P-type region. The current does not flow. In a diode, you also have a depletion region. This can be modeled as a parallel plate capacitor with a high value dielectric. We can use the comparison to model Zener breakdown. When a high voltage is put through the capacitor, the dipoles flip directions, as seen in the picture, and the dielectric will begin to act as a conductor. Similarly, in a diode, when the high enough voltage is applied, the electric field enables electrons to tunnel into the conduction band. This creates Zener breakdown. As mentioned previously, the rectifier performs the function of outputting the absolute value of its input. This function happens to fail both additivity and homogeneity. Thusly, the rectifier bridge of the circuit is nonlinear. For example, a sinusoidal wave is input into the rectifier, and that function was scaled to be the value of -1. The rectified output would not be scaled as -1. Rather, the output of the system would be the positive absolute value of the input. This shows that homogeneity is failed. For another example, let's say that we have 2 sinusoidal waves that have equal magnitude but are shifted by a period of 90 from each other. To pass additivity, the output should be 0, since the positive of one wave should cancel with the negative of the other wave. The rectifier, however, would produce a positive signal with a magnitude twice as big, because it absolute values the signals and then they would be added together and doubled. The rectifier is also time invariant. The absolute value operation that the rectifier performs does not actually change the time of the system, of the input or the output. A signal that was shifted by X amount of input into the rectifier would produce a signal that was also shifted by that same X amount. This would suggest time invariance. The RC circuit, unlike the rectifier circuit, is linear. It passes homogeneity. This is because a scaled input produces the same scaling output. So if you had a scaled input of X and you put it through a resistor and a capacitor, you get that exact same scaled value of X out. And due to the very nature of first-order circuits, the resistor and capacitor network has to follow the rules of additivity. Therefore, this circuit would be linear. The RC portion of the circuit is also time invariant. The time and shifted input to the circuit would produce a time-shifted output. Neither the capacitor nor the resistors would change the time input throughout as the voltage and current flow through the circuit. Overall, the RC circuit and the rectifier add together would result in a nonlinear time invariant circuit. So to summarize my findings in this KI video, we just learned out that a rectifier performs the operation of taking an absolute value of the input signal and turning that to the output signal. But we know that it cannot be modeled as an LTI system or a linear time invariant system because the rectifier breaks the rules of linearity, although it does follow the rules of time invariance. We also learned that a rectifier is used to make turn AC signals into DC signals, although it cannot truly make a DC signal. In fact, it does not make anywhere near to a DC signal. The output, to make the output closer to DC signal, an RC network must be applied. The capacitor smooths the rectifier output, and the bigger the capacitor is used, less total circuit output voltage will ripple. So the more precise your system is, you're generally going to want a bigger capacitor so the ripple voltage will be smaller and you can stay inside your tolerance for your output voltage. We also learned that a diode has an N-type and a P-type region that governs its forward and reverse bias behavior. We also learned that the diode's depletion region can be modeled as a capacitor to model Zener breakdown. I hope that you now have a greater understanding of the simple power management system I talked about today and the mechanisms of how it functions. Hope you have a good rest of your day.